Okay, welcome. So today's a day that I've been waiting for quite a while. We're going to go into chapter 2.3, cubic and quartic functions. So everything that we've learned up to this point, us studying limits and how to take derivatives and all that, will pretty much all culminate in this big unit. We're going to be learning about how we actually study functions, which at the beginning of the course, I think I said was the most important part of calculus at the high school level. Learning deeper about functions and studying what their shape is, and that's how we got into all that derivative tangent line stuff in the previous chapter. Okay, so let's begin. We're going to do, I think today is going to be mostly a content day, and then we'll get to some problems in the workbook. All right, so in order to properly analyze functions, we need to know a couple of terms up front. The first thing that we're going to be talking about is increasing and decreasing functions. What does it mean if a function is increasing or decreasing? Well, you guys have a pretty good idea about that, I think. So if we have a function or like a curve that goes like this, we define increasing or decreasing in the following way. We can take 2 points, 2 separate points on the curve. Let's call the x-coordinate of this one x1 and the x-coordinate of this one x2. And then here we'll have, I guess we'll call this f of x, and then we'll have f of x2 and f of x1 as our y-coordinates, okay? So let's say that if, let's say that x1 is always less than x2, that's how we set it up. There are 2 possible scenarios. If f of x1 is less than f of x2, we call it increasing. We call that the function is increasing. And if we say that, hey, in an opposite scenario, if we take the 2 points here and here, and f of x1 is greater than f of x2, we call that function decreasing. Now, we always call functions increasing or decreasing on an interval. Well, we don't always do that, since we learned about the instantaneous rate of change, but usually we put an interval around it. So if we set this interval like from A to B, we're going to say, hey, x1, x2 is going to be in that interval. Let's say, it doesn't really matter too much, but let's say closed interval, right? And if all of these are satisfied for every single possible pair, x1, x2 in that interval, then we can say that f of x is increasing or decreasing. So I'll just put a blank there on that particular interval that we set. So this is a formal way to define it, right? You take 2 points, you put them in order, and you see if the function value increases or decreases, right? So that's the mathematical way that we do it. Okay. But now, in the previous chapters, we learned that there's a way to find the instantaneous rate of change of something, right? So let's try to apply that through our derivative. So increasing means that, you see, for every possible point here, if we draw the tangent line at x, like at x1 and x2, and everywhere in between, the slope of the tangent line, the derivative, is always positive, right? Because the whole point of the derivative was to shrink these 2 points close together. So it would be no surprise that for every point on that interval, the derivative would be positive. So here we get another important way to classify increasing or decreasing. F prime of x is always greater than 0 on this interval. So that's how you would tell if a function is increasing or decreasing, by just looking at f prime of x. Here, decreasing, it would have an opposite story if we take the tangent line here, sort of like that, okay? The slope would be negative, which means that f prime of x would be less than 0. Okay, so it should say that in your note package. It says that the converse statement can be false. For example, x cubed increases on the set of all real numbers, but f prime of 0 equals 0. So just keep in mind that things can get a little bit finicky when the derivative actually equals 0. There's a concept called strictly increasing and strictly decreasing, but I don't think in high school you really differentiate, like tell them apart. So when the textbook says like increasing and it just says increasing, you can assume that there's no equal sign here. Because if there was an equal sign here, then it would also mean that like constant functions are both increasing and decreasing at the same time, and that's not what we generally use in a high school setting from what I've seen. So if it says increasing, you can assume that it's going to be, they call it strictly increasing. This does not have an equal sign in the inequality. But just note that for functions like x cubed, right, we want to learn more about this, but it has a derivative of 0 right at the origin point. But if you choose any 2 points, right, the definition is based on 2 points. So if you choose any 2 points, it's always going to be increasing, but the slope of the tangent line just at 0 is going to be 0. So I guess that's like just one exception where the opposite statement might not be true. But this is like just an edge case, so I don't think it would matter that much. Okay. So we learned about increasing and decreasing, and now let's talk about a very important concept that we'll be talking throughout this unit, which is the local minimum and maximum. Okay, you might have seen some problems while doing parabolas in pre-calculus 11. Find the maximum value of this function. Find the minimum value of this function, right? So this is a new term, local. Local means, like the word in English, local, it's around that point. So let's talk about this particular curve. Let's say I have a function like that, okay? What would be a local minimum and maximum, right? If these lines extend from negative infinity to positive infinity, if we assume that, then this function itself will not have a maximum or minimum value the way you would say, hey, this parabola has a minimum value here, right? But it does have local minimum and maximum values. So if we zoom into this sort of peak right here, right? I'm going to take this and I'm going to zoom in. It will sort of look like this broad curve, right? And if I take the very tip, the very top of that curve, you can see that at no other point in our defined interval is the function value higher than this top point. So that's actually the definition of a local maximum. For an arbitrarily small, so you can make your interval, I chose a very small interval, but you can go even smaller. For an open interval, no other, let's say this is x equals a, okay? So this is x equals a, x equals a. For an open interval, there is no x other than a, so that f of x is greater than f of a. Yeah, so everything in our chosen interval has to be less or equal to then f of a. So that means that this is going to be the very top of the curve, and you can zoom in on this interval however you'd like, right? So if we choose like a very large interval, then there might be some higher values up to the right. But the whole point of local minimum and maximum would be to get that interval small enough so only this part is isolated. So for one interval, basically it's enough. But you can see that visually, right? So the very top of a curve or the very bottom of a curve, right here we see a local minimum. So if we zoom in and choose an arbitrarily small open interval, there is no x other than a, so that f of x is smaller than f of a. That means that a should be the smallest value. And if you take a look at these definitions, then you might wonder, what about a constant function? If you just take these definitions alone, then technically a constant function at every single point on a constant function is a local minimum and maximum, just because of how the definitions are made, right? No other x value than your chosen point in that small open interval has any larger or smaller value than your function value here. So if the function value is the same everywhere, that technically means that every point on a constant function is a local minimum and maximum, but nobody asks that anyway, so that's just a side note. So these are how they're sort of formally defined here. But obviously, if you have like a curve like that, you can obviously see that, hey, this is going to be a local maximum. These are going to be local minimums, right? So the whole point is to get a visual intuition of increasing, decreasing, and what a local minimum and maximum is. They also call it relative minimum and maximum, and it means the same thing. Okay, so if we define the local, then we should define the global. So the global minimum and maximum is usually what you call, if you just say minimum or maximum, then it refers to the global min or max. And that means find the absolute, so that's another name for it, absolute minimum or maximum on the domain that the function is defined, right? So if we look at a function that's defined on the domain here, so let's say that it's defined on this closed interval, then I can spot some things, right? This is going to be the local, this is going to be a local maximum. This is going to be a local minimum, right? So, sort of those valleys and hills, if you would call it like that, of the function. So we can see that. But what about the global minimum and maximum, right? Global means everywhere on the defined interval. So that means the lowest that you can go is right here. So this would be the global minimum, right? And then what's the global maximum, right? The absolute highest that this function can go to on its defined interval would be right here. So this is the global maximum. So the global minimum and global maximum values would refer to the function values that these 2 points have, okay? So that means that if we are trying to find a global minimum or maximum, you would need to compare several things, right? First, you need to check your local mins and maxes, right? You need to check your local min or max values. And then the other thing to check is your endpoints of the interval, if your function has any. So if you're given a set interval, you should always check the endpoints of the interval, because although this is technically a peak of the curve, it is only a local curve. And in this function, this happens to be both the global maximum and the local maximum. But this point is a local minimum, but the global minimum is in a different place. So you need to compare the local minimum max and the endpoints of the interval. And what's the most efficient way to compare them all at once is to sketch the graph. So nearly all the problems that you'll be doing in this unit, I highly recommend you sketch the graph, because it's going to save you so much time and confusion. We'll get to how we actually do that later on. Okay, but now we need to think about how we're actually going to find the numerical values of these local minimum and maximums. Because this is just like an arbitrary, sort of abstract definition, right? You need to get a very arbitrarily small open interval. So how am I actually going to find the x values? Then we need to link all of this with the concept of the derivative, right? Okay, so if we take a look at any local maximum and local minimum, this is what we'll see. I'll use a green marker. Let's track the derivative at every point in our curve. So here the derivative is positive, 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 until we get to our local maximum. So that's the absolute peak of the curve, at which point it will be completely flat, right? If it was like not flat, then the function would still be increasing and there would be a point with a higher function value. And then right after the point where it's at the local maximum, the derivative will go negative, and then it will go negative. The function will decrease, right? Because a negative derivative means that your function is decreasing. And at your local minimum, your derivative will go from negative to 0 at that particular x value where the minimum occurs, and then it will go positive, right? Right now I'm going left to right. You'll usually go left to right because the x-axis will go in this direction. So here's the important thing. When the derivative equals 0, 3 things can happen, okay? 1, 2, and 3. In this function here, let's label what the sign of the derivative. The reason that we care so much about the sign is because if we want to tell if a function is increasing, decreasing, or not, we just need to look at the sign of the derivative, right? We just need to check if it's positive or negative. So here we have a positive derivative. Then at this point exactly, we have a derivative of 0, and then we go negative. And then at this point exactly, we have 0, and then we go back to positive, right? So when the derivative is 0 and the derivative changes, so if f prime x goes from positive to negative, let's say positive to negative, then this is going to be at a local maximum. So if you look around that point and the derivative changes from positive to negative at that point, it's going to be a local maximum. Likewise, if it changes from negative to positive, then we're going to have a local minimum. The third case is where the sign doesn't change. And let's take an example at that, right? The example that I'm going to give is x cubed. So this particular curve has a derivative of 0 at x equals 0. But as you can see, right around that 0, the derivative is positive, and then it goes to 0, but then it's positive again. That means that it's increasing, stopping for that instant only, and then still increasing, right? That means that it's neither a local min or max. Okay, so when we're trying to find local maximums and minimums, what do we have to do? We have to set f prime of x equal to 0. So that's the most important part. These points are going to be our points of main attention because that dictates the shape of the curve, right? But that alone, setting that equation alone isn't enough. We need to verify that the sign actually changes in some way to actually verify that, hey, is it going to be a local maximum, minimum, or is it just shaped like this, okay? All right, so we did increasing and decreasing functions, the definition of local maximums and minimums, the definition of global maximums and minimums, how to find the global maximums and minimums, and how to find the local maximums and minimums. And we've linked all that through the derivatives, setting them equal to 0, and seeing those particular x values. So these tools right here that are up on the board right now are going to be the very core of what we're going to be doing to analyze these functions, okay? Okay, so now I'm going to erase this and we'll move on to the cubic function. Okay. So in grade 11, you would have studied quadratic functions. They're often called parabolas because their shape is a parabola. And if you look at it now, it's kind of relatively simple, right? All you need to do is to find the axis of symmetry or your vertex. And if you have the vertex, you can write the function out in like standard form. You use completing the square to turn general form equations into standard form. You can use the discriminant to tell if it touches the x-axis at how many points. Yeah, so parabolas were, I think, relatively easier to analyze than what we're going to do now. But now we have the powerful tools of calculus to help us, so it won't be that daunting to us. Okay, so what are cubic functions? I think I told you the definition of a polynomial function back when we were doing limits and we were like, or derivatives, and we were proving the derivative of x to the power of n. A polynomial function is basically the sum of terms that look like this. You have a coefficient, you have x, and then you have a power to the n, where n is a natural number or 0, right? And if that n equals 0, that term would be the constant term. And you add up a finite amount of these terms, right? So there has to be a highest order term, and then there has to be the coefficient on that highest order term called the leading coefficient. So what are cubic functions? Cubic functions are defined as a polynomial function with degree 3. Ax cubed plus bx squared plus cx plus d, where, and this is the important part, a cannot equal to 0 because otherwise it would be a quadratic, right? So we've been dealing a lot with these cubic expressions. I think a couple classes ago we learned how to factor them using synthetic division and like how to solve cubic equations. And this is a cubic function. Okay, I'm going to show you what cubic functions look like, and then I'm going to explain why they look like the way they do. There are three main types of shapes that cubic functions can have, and they look like this, okay? Number 1, number 2, and number 3, okay? So let's look at the most complicated looking curve first. Number 1, if you say cubic function, this is going to be my mental picture, at least at first, okay? So this is what I would call the most common type, your average cubic function. Here, we're going to just assume for now that these curves are drawn where a is greater than 0. Your leading coefficient is greater than 0. If you can see why, in pre-calculus 12, you'll probably study exponential functions and like exponential equations, and you'll be familiar with the base functions like y equals x cubed. So this is the base function y equals x cubed, and you can check the shape, numerically, right? If I do 1 cubed, 2 cubed, 3 cubed, it will shoot up, and then if I do like -1 cubed, -2 cubed, it will shoot down to negative infinity. The thing to keep in mind is that a cubic function, so x cubed, will grow much more rapidly, especially at higher numbers, than any of these terms. Even if I have like a million x cubed, this function if I have a million x squared, 1 times x cubed will eventually win because you're multiplying the x value itself one more time, right? And here, if this was like a million or even like a billion, this number would stay constant and you're only multiplying your x twice. So a general rule of thumb is that the highest degree term is always the dominant term. And as you can see, for x cubed, and even like x to the 2n plus 1, where n is a natural number. So x to the power of odd, let's say, casually. If I keep increasing the function, it will shoot off to positive infinity. If I keep decreasing the x value, it will shoot off to negative infinity. So all of these cubic functions have that same, we call it end behavior, okay? In contrast, if we try y equals x squared, which looks like this, right? And x to the 2n or x to the even, they all follow the shape of this curve. They're not exactly the same curve, obviously, but they all follow the shape. As you go to negative infinity, the function goes to positive infinity, and as you go to positive infinity, the function also goes to positive infinity. So just keep this in mind, right? The distinction between x to the power of odd versus x to the power of even, and how the highest order term will determine the end behaviors. Okay, so we're focusing on cubic functions for now. The reason that a cubic function looks like this is pretty apparent when we take its derivative, okay? Taking the derivative of a function allows us to analyze if that is increasing, decreasing, what are the local minimum and maximum points, right? So that tells us a lot about our function than what we could do with like just regular algebra. F prime of x equals 3ax squared, right? Plus 2bx plus c. Okay, so now we got our derivative, and the first thing to notice is that we're assuming a is greater than 0 for these three curves, these three types. So if a is greater than 0, then 3a is also greater than 0. That means that this, if we draw the derivative directly beneath the function here, our derivative is going to be a quadratic that is concave up, right? It opens up. And as you can see here, we're going to mark where the derivative equals 0. In this function, I see 1 and 2 places where the derivative equals 0. And those 2 places are going to be, if we draw our derivative, these 2 x values are going to be literally the roots of the quadratic equation that is the derivative, right? So if we draw a parabola with a concave up function like that, remember that it's perfectly symmetric, so sort of like that. This is going to be f of x, and this is going to be f prime of x. As you can see, f prime of x goes from positive to 0 to negative to positive. Okay, so here the derivative is positive, right? It's above the x-axis. That means that your original function is increasing, and we can see that, right? It's always increasing until this local maximum point where it goes to 0, and then it changes from positive to negative. And then in this middle portion, it's all going to be decreasing, so it's always going to be negative, but then at this point, it changes from negative to positive, which means the function goes back from decreasing to increasing. Okay? So that's the thing to keep in mind here. It meets the x-axis at 2 different points. Now let's take a look at the second type of curve. Here, the derivative is going to be 0 at this point only. That means when we draw our concave up parabola, it's only going to touch the x-axis once, and it's got to be concave up, right? So it has to look like this. So it touches the x-axis at only one single point. Okay, how about the final cubic function? This cubic function does not have any single point where the derivative is 0. It just goes up like that, which means that the parabola cannot be touching the x-axis at any point. So it's a concave up parabola, so it has to be above the x-axis. And you might say, you might wonder where the axis is located. Here, it's actually a sort of a distinct curve. It has a slightly like this part and this part combined, and the exact point where it switches the curvature is going to be your axis. And we'll talk briefly more about that in a little bit. Okay, so now you know what the three types of cubic functions look like. It's either this with a local maximum and a local minimum, or this with just one point where the derivative is 0. This curve and this curve does not have any local maximums or minimums, right? And this final curve does not have any points where f prime of x equals 0. So here is f and here is f prime. And I said that the discriminant of this parabola has to be larger than 0, discriminant equals 0, and discriminant is less than 0. Okay, cool. I want to tell you more about cubic functions, so let's do that. How do we set up the equations of cubic functions? So now we learned the shapes, right? So how do we set up the equations? Keep these images in mind, okay? Let's say that we factor a polynomial function and we get it factored, right? So it's like there's a lot of factors involved. Let's say x minus alpha, x minus beta. Let's talk about that. Let's talk about the power on the x minus alpha term. Let's say that this power is even. So x minus alpha to the even power is in the factored form of an equation, let's say. Okay. Then what will it look like? I can compare the limits as x is slightly larger than alpha and x is slightly smaller than alpha. When x is slightly larger than alpha, this is going to be slightly larger than 0. So if we look at the even curve right here, this is going to be slightly positive. And if we go slightly less than alpha, so slightly less than 0 in this term, it's still going to be slightly positive. And the remaining terms aren't going to be affected, right? Because they're a different number. They're not going to go near 0. So the remaining terms have a constant value, but just the sign, we just need to pay attention to the sign of this expression. Here, no matter if we're slightly above or slightly below 0, the sign of the function value is the same, which means in the outcome curve, well, the sign of the curve will not change, the sign of the function value. So that means either we go positive to positive or negative to negative, like this. It will touch the curve and then it will curve back. So it will go from positive, 0, positive to negative, 0, negative, something along these two. If we have an odd power, though, then it gets different. Because if we have x minus alpha, and x is slightly larger than alpha, you can see from this graph that it's going to be positive. But if we go slightly below 0, then it's going to be negative. So the sign of this function near alpha will actually change. If the power is 1, it will go straight through. Okay, so power equals 1. But if the power is not 1, remember, if we take the derivative of this expression and we use the product rule, then we'll always get at least an x minus alpha term if this is greater than 2, right? Because the derivative of x minus alpha is 1, but the derivative of x minus alpha, anything to the power of like something higher than 1, we'll have to use the chain rule. So there's an x minus alpha remaining, which means that the derivative will still be 0, but it will have to change signs, either like this or like that, depending on the situation. But just keep that in mind, that if we have an even power, it will spring back. If we have an odd power in the factored form, it will go through. So using these basic facts about polynomial functions and the stuff that we know about cubic functions, we can set up the equation basically in every single scenario. So I'll present to you a couple of examples, and then you can follow along and see if that logic makes sense. The very important thing is that we're getting the logic here. We're getting why they look like the way they do, and how are we going to represent them algebraically. So in this example, let's say I have a cubic function that looks like this, 1, 2, and 5. And let's say that for example's sake, the leading coefficient is always going to be 1. Or we can set it as k, I don't know, whatever. Okay, so first thing to notice is I have a cubic function with a positive leading coefficient. If it was a negative leading coefficient, it would go from positive infinity to negative infinity, like that. But we don't have that right now. So we're going to assume a positive leading coefficient. Well, we know that, right? And we have the roots. We have 1, 2, and 5. And as you can see, they're all going through. So they have to have a power of 1 each, because the maximum power you can have is 3, right? And you have 3 roots. That means it's simply going to be x minus 1 times x minus 2 times x minus 5, right? And then we'll put a k in front of it, where k, we know that k has to be greater than 0. There we go. You just express this curve algebraically. So that's how you would do it. Okay, how about this particular curve? So here we have a cubic function that's, let's say it's 1 over here and, I don't know, 6. Let's do 6, like that. How would we represent this cubic function? Well, we know that it goes from positive infinity to negative infinity, so it must have a negative leading coefficient. We have a root with multiplicity 1, right? So I talked about power here. The official name for that is the multiplicity of the root. Multiplicity. A multiplicity of 1, so multiplicity of 1 is known as a simple root. And all the others above 1 are known as a multiple root or something like that, right? But a multiplicity of 1 is a simple root, so I'll refer to that terminology. So this is a simple root, so I can go f of x equals, let's do negative 1. So remember, when we're setting up roots, we gotta write down the opposite sign, right? Because the whole point is that we're trying to find numbers that would make the expression 0. So we gotta go with the opposite sign. So let's do k, x plus 1, and then x minus 6, but you see how it's curving away, right? It jumps back. So this must have an even exponent, but an even multiplicity. The highest degree is 3. We must have a degree of 3, right? So that the only option for this case would be a degree of 2, which means that degree of 1 multiplied by a degree of 2 would get you a cubic function, where k is less than 0. So this would be your expression for this particular cubic function. How about this? Okay, 1. Here, we only have 1 root, so f of x would be k times, we know that k is positive because it goes from negative infinity to positive infinity, x minus 1, it has to be an odd power, but it has to be cubic, so it has to be 3. And you'll also notice that the derivative is 0 here, and for simple roots, the derivative is not 0. Okay, so for k is greater than 0. So you looked at a couple scenarios where we could simply set up the equation. Just remember where it intersects the x-axis, it's going to be the roots, and then those powers on the roots, the multiplicity of the roots, will be based on this type of geometry near the x-axis. Okay, cool. Now I want to tell you a pretty cool trick, or like a pretty cool fact, I guess. Not so much of a trick, but I'll erase the board. I'll erase like half of the board. when we study like something like circles, right? We we sort of memorize their fundamental geometric properties, like the tangent line to a circle has to be always perpendicular with the radius, stuff like that. And when we study parabolas, we also study about its symmetry, about its x-axis. So let's study about the geometry of cubic functions. You might think that, hey, is there a geometry in this complex cubic expression? Yes, there's a couple of noteworthy things to talk about. Okay, every cubic function that we talked about is point symmetric. Okay, let's talk about this. A point symmetric shape is where you have a point, and then for every point outside of that symmetry point, you're expected to have another point on the shape so that it's equal and opposite, basically, to the point of symmetry. So if I draw something like this on one side, then it has to mirror the shape on the other side. So if I pick any point, the other point must lie equal and opposite to the point of symmetry. And look at the figure that I just drew now. It sort of looks like a cubic function, right? All cubic functions have a point of symmetry. Okay, so let's draw the three types of curves again. And this point of symmetry, specifically in cubic functions, is called the point of inflection. Now, when you go to a regular calculus course, you'll talk more about like what exactly a point of inflection is, and you'll relate that to like the concept of a second derivative. But for our course, for now at least, before we go on to like quartic functions, we'll treat the point of symmetry as point of inflection as the point of symmetry in cubic functions. So this is called a point of inflection. Okay. So what's going on here? If I grab a point on the cubic function, and then I pass that line through the point of symmetry and go equal distances, then it will always land on the graph again. So for every point that I do this, there will be another point on the curve that is equally distant and opposite to the point of inflection. Why, you might ask? The original x cubed, it might be worth discussing. Yeah, it might be worth discussing this. Okay, even in odd functions. We're going through a lot of content today, but I feel like it is important to know these baseline concepts. So let's talk about them. Okay. An even function and an odd function let's talk about their definitions first. Even functions are functions where f of negative x equals f of x for all x. That means, right, let's think about it visually. If we have a function that has a function point here, if we have a point here, then f of negative x should be equal to the function value of this. So we go right across the y-axis and put another point here. In the end, every point that we have on the function must be symmetric about the y-axis because the function values have to be similar, has to be the same, right? So that means any function that is symmetric about the y-axis is an even function. And the definition of an odd function is f of negative x equals negative f of x. So now you see there's a sign change here. So maybe you can memorize that as a sign like crawling out. So let's think what that means visually. So if we have a function value here, then if we go from x to negative x, then the y value should be the exact opposite. It should switch signs. So that means we should have a point over here. So that means that for every point, we should have a reflection against the y-axis and a reflection against the x-axis as well. So that means, if you remember in transformations, if you flip about the y-axis and you flip about the x-axis, that means that you're symmetric about the origin point. So maybe a function that looks like this would be an odd function. So geometrically, that means symmetric about the origin point. So an odd function implies point symmetry. Well, if you say odd function, it must be reflected against the origin point. And an even function is reflective against the y-axis. Okay. Now let's take a look at this here. This isn't exactly an odd function because we don't know where this inflection point is going to be. But if we take an even function, we know that parabolas are going to be even, right? Well, it would be easier if we move the point of inflection down to the origin, right? Okay. Sort of like that. If we translate the graph down to the origin point, the derivative is going to be like that, with the axis of the parabola directly on the y-axis. Why? Because it's the exact midpoint of the local minimum and local maximum and minimum. So everything's going to be symmetric with each other. So technically that point goes over here and this point goes over here, slightly misaligned. But this is symmetric about the y-axis, which makes it even. And an odd function, if you go backwards, has to be... Okay, let's not talk about going backwards because that's going to be the next unit. Let's talk about going from odd to even. If we look at this expression and then we take the derivative of it, that actually ties very nicely. If we take the derivative of it, we're going to get f prime of negative x. And then we're going to get the negative sign because of the chain rule equals negative f prime of x. And if we look at f prime in this case, right, they both have negative signs, so I'll turn them into positive signs by multiplying -1. F prime of negative x equals f prime of x. That means that the derivative of an odd function is even, and the derivative of an even function is odd, right? If we take the derivative, it's going to be negative f prime of negative x equals f prime of x. And that would be the exact definition here, right? If we just switch the negative signs. These are good things to know. The derivative of an odd function is even, and we know that if we translate this over to the y-axis so that the inflection point is on the y-axis, the derivative is going to be an even function because the parabola has an axis of symmetry right on the y-axis. Its vertex is directly on the y-axis because, as you can see, the steepest tangent line that we can draw. So we're slightly doing the derivative of the derivative, if you get what I'm saying. But we don't need to go there. You can visually see that the steepest that we can go in the negative direction for the tangent line, the steepest negative tangent line is right through the point of inflection, right? If we go slightly to the right, we'll get a shallower curve. And if we go slightly to the right, we'll get a shallower curve. That means the steepest value, so the lowest value of the derivative has to lie right on the inflection point. So that's where the curvature changes, I told you, right? So that's why f prime of x is even, and if we know that the derivative is even, the original function has to be odd, which means that this original function, if we place the point of inflection right at the origin, if we translate it down, that function will be point symmetric everywhere. That means that if we just translate it back to wherever we were here, that point symmetry also still holds, because although an odd function implies symmetry about the origin point, even if you translate that function anywhere, the symmetry is still going to be held the same, okay? So if you understood that, good job. You're thinking way ahead. If you don't understand that quite now, it's okay. We'll revisit this geometry concept many times, and if you stick around till unit 3, you'll even get like a better picture, in my opinion. Okay, the important thing to know now is that every cubic function does have a point of inflection where the curvature changes like that, and it's all symmetric about the point of inflection. And the tidbit that I said about this being the maximum negative slope, or in like a decreasing cubic function with a negative leading coefficient, the tangent line through the point of inflection is going to be the steepest positive slope that you'll see in the entire function. Many people just like look over that, but some really quite difficult problems might exploit this fact. Okay, so they're all symmetric, which means they're equally distant to each other. Okay, so we got that. On the point of even and odd functions, if you want a concrete example of an even function, then you might want to look at x to the power of even, right? I think that's where the name comes from polynomial functions. But even if the functions are not polynomial, as long as they satisfy these criteria, then anything could be an even or an odd function. The properties, I said that the derivative of an odd function is even. We can see that, right? The derivative of like x to the power of odd, the power goes down by 1. If you go down by 1 from an odd number, it's an even number, and vice versa. There's also this cool property. I guess it's pretty evident from like these definitions. If you do odd plus odd, then the function will still be odd. If you do odd plus even, even plus even, the function will be even. So let's say you have the function x to the power of 10 plus x squared. Each one of these satisfies this individual condition, and if you add those two, the equality will still hold, right? That means this is purely an even function, and stuff like x to the power of 3 plus x is also going to be an odd function. So if you add odds together and evens together only, you'll be guaranteed an odd or even function. Anything other than that, you don't have a guarantee. Okay, I think these are the basic properties to take note for now. And I'll tell you one more secret. Okay. I'll erase this middle part, okay? There are many, many, many cubic functions, But underlying those cubic functions, there are a couple of fundamental ratios. Okay. I'll call them special, what do I want to call them? I'll just call them special ratios. Okay, I'm going to set up a very specific situation. Just follow me for a second. Let's set this up here. Okay, let's call this 0 and let's call this 3 alpha. You'll see why I'm putting a 3 in front of it later. But let's say we have a 0 and we have a 3 alpha. Now we know how to set up the equation of the curve, right? So let's say this is f of x, and we'll say f of x equals, hey, k is positive, then we're going to go x minus 0 squared, right, times x minus 3 alpha. And we can write this out. Kx cubed minus 3k alpha x squared. Now we're going to take the derivative to find our local minimum point over here. F prime x equals 3k x squared minus 6k alpha x, and that has to be equal to 0. So we can factor out 3k, that will be 2. We can group by x. Remember not to cancel it out when you're solving equations unless you know that it's not going to be 0. X minus 2 alpha equals 0. X equals 0 or 2 alpha. And as you can see, x equals 0 we already know, right? Because it's a local maximum. It's always in order, right? And x equals 2 alpha is here. And remember, when we took the derivative, I told you guys that the point of inflection would be the very bottom of this parabola, right? In this case, right? Because it's the slope of the tangent line would be the steepest at this point. And the function has point symmetry, right? So this x-coordinate of the point of inflection would be exactly the midpoint of these two x-coordinates. So this will be alpha, okay? And if I draw another line down here, then what we'll see is that by point symmetry, the distance between this point and this x-coordinate is the same from here to here. So the difference in x-coordinates here is from alpha to 3 alpha, so that's 2 alpha. If we go back, this will be negative alpha because we're going 2 alpha back. And as you can see, if I just take this away, all of these distances are the same. And if I draw a line parallel to the x-axis, like that, then by point symmetry, the distance here and here would be the same. So if I take the coordinate system away, that was for the convenience of calculating, simplifying our calculations. If I take the coordinate system away and just look at the curve itself, if I draw the horizontal tangent line here and here, and I draw these vertical lines at each of these points, including the point of inflection, then these lengths will always be the same. And that is a great fact to know, and that will save you a lot of time based on my experiences. So let's go back to an example that we were doing. I'll give you a new example. If I have a cubic function like this, and I say that, hey, this is 2 and this is 8, can you find me the x-coordinate of this local maximum? What you would normally do is you would set up the function x minus 2, x minus 8 squared, and then take the derivative using the product rule, and then setting that product rule derivative equal to 0 and solving a quadratic equation. And you have to do all that algebra. But if you remember this ratio, 1, 1, 1, right? Because you have to include this point of inflection. The distance between these 2 points is 6, and then if you divide that by 3 spaces, it's going to be 2. So all you have to do is add 2 from this point, and you'll get 4 instantly. And I think that's just like a huge time saver when you're dealing with these functions. Yeah. So I do want you to memorize and take note. You have been taking all the diagrams down, right? I know there's a lot of content today, but these are all really helpful if you have all of these in your like toolkit, right? Recognizing when functions are even and odd, recognizing point symmetry, and using these special ratios to your advantage. I think that's really nice. Okay, I have one more special ratio to show you for cubic functions. Okay. I'll call this the 1 to 1 to 1 to 1 ratio. There's a second ratio, and that has to do with the point of inflection. All right, so I'm going to restructure my axes so that the origin point is exactly at the point of inflection, sort of like the way we did it here. So this is my new coordinate system, and I'm going to, okay, I'm going to set this guy as alpha. Okay, I'm not going to spoil the coefficient here. All right, I'm going to set this as alpha. That's fine. Due to point symmetry, right, this is going to be negative alpha. So I can set up my equation. F of x equals k times x minus alpha, x plus alpha, and that will go to kx, x squared minus alpha squared, which is kx cubed minus k alpha squared x. And I'm going to take the derivative to try to find this local minimum point. F prime of x equals 3 kx squared minus k alpha squared equals 0. We can factor off the k. 3x squared equals alpha squared. X equals 1 over square root of 3 alpha. 1 over square root of 3 alpha, which means that the ratio from here to here is 1 to square root of 3, right? Because you multiply this fraction by square root of 3 to get 1. So that's the second ratio that I feel like it's not as helpful, I guess, as this one, but still a good one to know. So if I just take the coordinate system away and I draw the axis through the point of inflection, and I label the point where it's at a local maximum or minimum, the ratio here is going to be 1 to square root of 3. So what I want you to remember is definitely the 1 to 1 to 1 to 1 and the 1 to square root of 3 ratio. These are just really helpful things to know about the geometry of cubic functions. A final thing about the geometry is let's go back to point symmetry and let's draw the derivative. As you can see, the derivative has an axis that's at the point of inflection. So and we know that parabolas are symmetric about their axis. So if I take any 2 points that are equally distant, like from in the x direction from the point of inflection, and I take the derivative at these 2 points, their derivative values, right, because it's a parabola, are exactly going to be the same, right? And that includes this part, this function, and this function as well. because the actual function value doesn't matter, doesn't take into account like, hey, where is the x-axis, right? So for any two symmetric points on your function, the derivatives are going to exactly match each other. Okay, I think one more thing and then we'll be done with the content for cubic functions. But this final thing is more general as well. So what I'll do is I'll erase the second ratio and then I'll place the final topic in this space. Okay. The final thing I want to talk about is the difference, the importance of setting up difference functions. So what does this mean? Let's say that you want to find the intersections between two curves, okay? Let's say you have a quadratic, in general, this is a good strategy. If this function is f and that function is g, when you're trying to analyze these intersections, you should always, what do you do in algebra, right? You set them equal to each other, f equals g, but once you actually solve it, you put everything to one side, right? You put everything to one side, f minus g equals 0, and then you solve for the intersections. In our cubic function context, let's say that, hey, I have a cubic function like that, and then this line is the line y equals like 5, okay? How are we going to set up the equation if we say that this is 1 and this is 3? The x-coordinates, I mean. We're going to think about the difference function. If this is f of x, we're going to technically, the roots of the equation f of x minus 5 equals x minus 3 times x squared times k, right? I'm just going to omit the k for now, okay? Because that doesn't really matter too much. The difference function, so if we subtract f of x, if we subtract 5 from f of x, we'll get this equation. Which means that if we want to look at the original equation, this is going to be x squared x minus 3 plus 5. So that's going to be your reference line, right? How about this? This time, I have a line g of x, and it's meeting here at, like, it doesn't really matter, but like, let's keep 1 and 3, like that. How will we set up the equation of the cubic function? Again, we think about the difference function, right? So f of x minus g of x has to have the roots 1 and 3. So let me just draw. It's really important that at the beginning you try to draw it out as much as possible. As you become more comfortable with these mechanisms, you'll be able to, see these things in your head mentally. But it's always important to understand what's going on. So the difference function will still be a cubic function, right? Because if you subtract a monic expression from a cubic expression, it doesn't erase the cubic expression. If we take the subtraction, if we take let's do g of x minus f of x. What will that look like? In this portion, g of x is always above f of x, so it will be negative. Here, they will equal each other. But that means if we take the derivative of this is g prime minus f prime, right? And here, the derivative of f is exactly equal to the slope of g because g is this tangent line at this point. That means that we'll have a derivative of 0 here, and then it will decrease. And then it will increase again here. Does that make sense? Because in this portion, from here all the way over here, g of x is lower than f of x is lower than g of x. That's why the function is all negative. And then at this point, f of x will actually go up above g of x, which means that the difference, so the subtraction function, is going to be positive. And it's much easier to analyze horizontal lines, right? Horizontal lines, because they're simple in their equation, right? Than trying to analyze a slanted line. So if you're given in a problem like, say, hey, the slope of g of x is like 1, and you're trying to analyze if it meets or not, maybe it's a good idea to set up the difference function and solve it like this, right? Let's do one final example, so that we get the straight y equals -1, we have x equals 2 and 4. Okay, so first we're going to set up x minus 2 squared, right? And this is a good idea to apply our 1 to 1 to 1 to 1 ratio, right? So it's 2, 1, 1, and 1, right? So the distance between them is 2, which means that we need to go 1, 1, and 1, so that this is going to be 5. X minus 5, and then we're going to ignore the coefficient for now. Just say it's 1. Plus, and then it's going to be -1, right? So we're going to do this, but it's going to, our reference point is going to be -1. Right? That's because if we actually set up the equation f of x equals -1, f of x plus 1 equals x minus 2 squared, x minus 5, so f of x is going to be this -1. But here we can sort of intuitively set our reference here and then write down the equation and then write down our reference. So everything is going to be like shifted down by 1. You can also think of it like that. Okay, if we take a final look at our special ratios here, our special ratios also apply in the context of this as well, right? Because in the end, if we subtract the line from the original function or vice versa, we're still going to get a cubic function, right? Oh yeah, here it's not, I wrote it opposite, right? It's f of x minus g of x, because we're subtracting the curve from the, we're subtracting the line from the curve. And then its derivative is going to be f prime of x minus g prime of x. So when their derivatives equal each other, they're going to have a root here. When their derivatives equal each other, they're going to have the difference function will have a derivative of 0. So it will be like around like that point where the derivative is 0. And then if we apply this situation to our ratios, if we have a tangent line that's slanted like that, we know that as long as we have another parallel tangent line this way, that's parallel to the original tangent line, and then we drew this vertically because we're only like slightly warping the tangent lines. The actual y values, like say, we're keeping the same, right? Because when we take the difference function of this curve and this line, it's going to end up like what? It's going to end up like this, right? 1, 2, 3, 4, like that. So that means that your x coordinates are going, your x, these lengths are still going to stay the same. If we draw it like that. So it's only an offset like that. And by similar triangles, these lengths are also going to be the same. And similarly, the ratio through the point of inflection is still going to be 1 to square root of 3, because if we extend these vertical lines, our original difference graph had the ratio 1 to 3. So it doesn't matter in the end if your reference is like a slanted tangent line or a horizontal tangent line. The ratios still hold, and that's why they're pretty useful, as you might see in some of the upcoming problems. Okay, I think that was like a lot of content. So I'll actually leave it there for today. Let's see. the homework. I think quartic functions don't appear until number 14. Yeah. So today, I'll just leave you with this to think over. Obviously, next time, we'll go over, we'll start with the workbook questions, okay? I think that would be the way to go here. So, yeah, this is how we are going to analyze these functions. Just take a note of the different things that we've covered today, like increasing and decreasing, local min-max, global min-max. How does a derivative of 0 matter? If it changes from positive to negative, it's a local max. Stuff like that are the core. These ratios, honestly, I really encourage you to memorize these, but like these are not that important. But we talked about like even and odd functions. I think that's a pretty important concept, and the importance of simplifying like these complicated situations into more manageable ones by taking the difference of the two functions. I think like setting it up like this is a pretty important skill to have, because your reference like line for cubic functions will not always be 0. Okay, I think that's it for today. So next time we'll start with the workbook questions for this chapter. All right, thanks for watching.